Hi guys. In this video, I want to talk you through how to apply Kirchoffs loop rule to two simple examples. So we have here is two resistors in series. This is a lamp and this is another lamp. And they're not supplying voltages, they're kind of using up the voltage, so they're equivalent to just like a regular resistor. The fact that they're producing light doesn't really change anything. So I'm going to call this one resistor 1, and then I'm going to call this one resistor 2. And I'm going to say that this is V total from the battery. And we're going to develop a couple of tools over the course of this unit, but if you want to just apply Kirchhoff's loop rule to this circuit, how would I relate the voltages across the battery, VT, this one, the voltage across this lamp, V1, and this one, V2? Take a second, see if you can write out an equation that relates those voltages. So think back to that graph. If I'm at the negative end of the battery, I'm starting at 0. As I go across the battery, I'm going up 9 volts. The wire doesn't do anything, but as I drop across the bulb, there's the drop. Wire doesn't doing anything, drop across the bulb. So how do I relate those voltages? I know that this is VT, and this drop right here is V1, and this drop right here is V2, where those V's are rarely representing just the size. So if I want to write it as an equation, it's an increase of Vt minus V1 minus V2. What's that going to get me? By the time I've dropped to V2, I'm back to where I started. I've gone in a loop, so that's why I know that that's how I'd relate those voltages. In this particular diagram, I'm given this voltmeter, and this voltmeter is measuring the voltage here. So I actually know that V1 is the size of it is 4.5. So don't really get so worried about the size. If I swapped the ends of this voltmeter, the sign would reverse. You need to, I guess, just keep track of the size across this and know that if I'm writing a loop rule equation, that as I'm going from the negative end of the battery to the positive end, that's like a voltage increase, and then it's a drop back to 0. So you just try to keep track of that in your head. Don't worry so much about the sign here. So anyway, just to solve for V2, that's the only unknown. So V2 is equal to VT minus, and so that is 9 volts minus 1. My pen, I don't know if you guys can see this. Came out a little weird, but take it. And that is equal to volts. So that's VT minus V1. 9 volts minus 1.5 is 4.5 volts. So that's the voltage across 2, but I was also asked to find the current. So that's when I'm going to go to my handy Ohm's law. There's this nice little VIR table that I can make, VIR, for resistor 1 and resistor 2. I can just label the voltages if I know them, or the currents, or the resistances, and solve for the unknowns. So the voltage across resistor 1, I was given that that's 4.5, and what I just used the loop rule to solve for was that V2 is also 4.5. And the resistances are shown in the diagram. That's just 10. And so do you see how to solve for the current? That one's just Ohm's law. V equals IR. I'm going to take this 4.5 divided by the 10. That's a 10, by the way. And I'm going to get 0.45. And the current is also going to be 0.45. You should be a little bit more organized in your table. Just hard for me as I'm doing this electronically. So there, I've solved for I1 and I2, and I properly applied Kirchhoff's loop rule. Let's go to the next one. So for this next example, it's two resistors in parallel. Take a second, can you write out the loop rule for this circuit? And actually, there are two. So if I'm going to call this one 1, and then this one 2, and then this one VT, it's the scenarios we looked at before. If I'm to write out the loop rule, I start here, plus VT minus V1, and I'm back to 0. So VT minus V1 equals 0. I could also write out the other loop, and that is plus Vt minus V2 is equal to 0. So from this, I'm also seeing that, oh, V1 and V2 are equal. I could do a loop rule equation starting from here. This would be a minus, let's say, V2 plus V1, and that's equal to 0. So the loop rule doesn't have to start and end of the battery. It's true for any loop, which is kind of why it's cool and powerful. So right there, I solved for V1 and V2. I'm going to go to my handy VIR chart. It's a little squished here, but that's okay. So the voltage across the battery was 9 volts, so V1 and V2 are going to also be 9 volts. So this is, let's say, for resistor 1, and that's for resistor 2. Nice. Those are 9s. And I'm told in the diagram that the resistance is 10. So now I can use Ohm's law to finish this up. V equals I times R. So V over R is going to get me my I. So the current is 0.9. And it's 0.9 for both of them. Same math. So I solved for what I needed to, and these are the two loop rule equations that describe the circuit. Hope that was helpful. Take care.